We represent compounds with chemical formulas. In the chemical formula, we're indicating what elements are present in that compound and how many atoms or ions of each there are. So we do this using subscripts. So, for example, water is H2O, which reminds me of a joke a little old lady at the nursing home told me on Sunday. If water is H2O, what is H2O for? Drinking, bathing, swimming, right? What is H2O for? F-O-R? Yeah. I was just like, I love that old lady. Okay, anyway. So H2O, we put a 2 subscript after the H to indicate that there are 2 atoms of hydrogen, and there's 1 atom of oxygen. We don't write the 1. Chemists seem to have a thing against writing the number 1. If the element symbol is there, that means there's 1 atom or ion of it. If there was more than 1, we'd write the number. If there were 0, we wouldn't write it at all. Another example, carbon tetrachloride, CCl4. So there's 1 carbon atom, 4 chlorine atoms. Any questions? We can write different types of formulas, and these give different amounts of information. The simplest formula is an empirical formula. Empirical means it's derived from experiment or experience. An empirical formula just gives us the relative numbers of atoms of each element in a compound, not necessarily how many atoms are in an actual molecule. So an example, let's look at hydrogen peroxide. So the formula, well, let's try it a little different. I know what I'll do. I'll draw pictures. There's a bad picture of hydrogen peroxide. That's the molecule has 2 oxygen atoms and 2 hydrogen atoms. So we would normally write that formula H2O2. That's what's called the molecular formula. It tells what's actually in the molecule. The empirical formula gives relative numbers. So we look at the ratio here of 2 to 2, and we simplify that. The lowest ratio is 1 to 1. So the empirical formula for hydrogen peroxide is HO. The simplest form, okay? So it's just like taking a fraction like 2 halves and reducing it. Well, that would be 1 over 1, right?
You said it gives the what?
The relative number. Yeah, it doesn't give the actual number. And we'll learn a little more about this, but when you do an experiment, you take a compound and maybe separate it into its elements and weigh the elements, you can find the ratio of atoms of hydrogen to oxygen, but you can't tell from an experiment like that how many atoms are actually in a molecule. That requires something else like a mass spec. So the molecular formula gives the actual number. So here are 3 different molecular formulas. C4H8, that molecule has 4 carbon atoms and 8 hydrogen atoms. From that, we should be able to write the empirical formula. We just simplify. So ratio of 4 to 8 would be a ratio of 1 to 2. The empirical formula is CH2. B2H6, 2 borons, 6 hydrogens. That can be simplified to BH3. CCl4 is a molecular formula. The ratio there is 1 to 4. Can we simplify that? No. So the empirical formula for carbon tetrachloride is the same as the molecular formula. Sometimes they're the same. But that's the difference between an empirical and a molecular formula. There are also structural formulas. And these show how the atoms in a molecule are connected or bonded to each other. And they often specify the type of bond, whether it's a single, double, or triple bond. So a single line for single bonds, a double line for double bonds, a triple line for triple bonds. That makes sense? Which formula we use depends on what we know about the compound and what we're trying to communicate to other people. The structural formula gives the most information, but especially for larger molecules, it can be very tedious to draw out. The empirical formula gives the least. So write the empirical formula for the compounds represented by these molecular formulas. So what would the empirical formula for C5H12 be? It'd just be C5H12 because you can't divide 5 and 12 by the same number and get a lower ratio. That is the lowest ratio. How about Hg2Cl2? Stage GCl. And how about C2H4O2? CH2O. This empirical formula tells us the ratio of carbon to oxygen is 1 to 1, and there's twice as many hydrogen atoms as there are carbon or oxygen atoms. We also use models. Molecular models give us more information than just the formula. One is that we use a lot is a ball and stick model. So we represent the atoms as balls and the bonds as sticks. It's a little bit like a scientist's Tinker Toy set. They're actually kind of fun to mess around with. We use colors to indicate different elements. You don't need to memorize these, but just be aware. There's a reason that every time they draw water molecules in the textbook, the oxygen is red and the hydrogens are white, because there's this kind of code. It just makes things easier. And then there are also space-filling models. So this is the ball and stick model. This helps us to understand the shape of the molecule and how things are connected. That's not how a molecule really looks, though. There are not big spaces between the atoms. This is more like what an actual molecule would look like, where they kind of overlap with each other and they squish into each other, okay? And that's possible because atoms are mostly empty space. And so when they're sharing electrons, they're sharing that mostly empty space and they will overlap with each other. So here we have the molecular formula, the structural formula, ball and stick model, space-filling model for the same compound. Here's a table from your book just showing all of these different things for 4 different compounds. This is glucose. Empirical formula is CH2O. The actual molecular formula, though, is C6H12O6. You can have lots of different compounds with the same empirical formula, but their molecular formulas may be very different. If we look at the space-filling model, if that's all you had, you probably would not get the right number of oxygens or hydrogens for sure, because you can't see what's on the back side of it, right? And so the ball and stick model makes it easier to see from all sides. This is much easier to put on paper than drawing circles and sticks. So they have different uses.